In the previous section, we discussed writing to and reading from a DMA FIFO. By the end of this module, you will be able to handle DMA FIFO underflow and overflow conditions. In this section, we're going to talk about underflow and overflow and how you would handle each of those. Okay, so first let's talk about underflow error. If the DMA FIFO read is configured to read n elements and times out before n or more elements is available, the DMA FIFO read returns error -50,400. Okay, so if you take a look at that screenshot at the left, notice that on our host VI, if we're trying to read from that DMA FIFO, we're trying to read 100 elements, and we have a timeout of 1. So let's say we get to this node, and there's not yet 1,000 elements in the FIFO yet, and then 1 millisecond passes. So in this case, there's an underflow, right? Because we weren't able to get 1,000 elements by the time this node timed out. So what would happen is on the output error wire, it's going to contain error code -50400. If you're checking for that particular error code, then you can see that there's an underflow error. So typically in most applications, if you have underflow, it's not super critical. So what you could do is, if you have something like this in your application, you can just discard or ignore -50400 as an underflow error if you expect that you might get some and you know that you don't want your application to stop because of it. One thing I want to note, if you look at the block diagram on your right, so this was the recommended way that we suggested that you read from your DMA FIFO on your host. So if you use this method, you actually will never get that -50400 underflow method. And the reason for that is, if you look at that first DMA read in that while loop, it's always checking consistently for how many elements are remaining, and we're checking to see if it's reached our fixed size. In this case, we're looking for 10 elements. And our DMA read, that second one, is only going to read when it knows for sure that there's at least 10 elements in the FIFO that are available for reading. Okay, so if you're using the method on the right, then you really don't need to worry about this underflow error. Okay, let's talk about overflow and preventing overflow. So an overflow happens when the DMA FIFO is filled as a result of the data being written faster than it is read. And at this point, data might be lost. So if you have a DMA FIFO and it fills up because you're writing a lot of data to it and you're not reading from it fast enough, well, the FIFO is going to be full, and then the next time you're trying to write something into the FIFO, for example from the FPGA, then that data is going to get lost. And then we can find out if there's an overflow condition, and if there is, then we know that's bad news. Okay, so how do we prevent overflow from happening in the first place? So if you're getting overflow errors, you might want to reduce the rate at which you write data to the FIFO. So if that's acceptable for your application, if you reduce the rate that you're writing to the FIFO, then you're slowing down how fast that DMA FIFO is getting filled up. So that could solve the problem. Another thing you can try doing is you can increase the number of elements to be read on the host. So if the host is only reading 5 elements at a time, so it's only grabbing 5 elements out of that DMA FIFO at a time, maybe you want to increase that to 100 or 500 or more. And that way, if the host is grabbing more elements out of the DMA FIFO each time, that DMA FIFO might not fill up so fast. Also, you can try increasing your FPGA buffer size and your host buffer size. By increasing the buffer sizes, it gives you a little bit more leeway when you're doing your DMA transfer. However, if the speed is just coming in too fast and you're not pulling things out fast enough, then increasing the buffer sizes aren't going to help that, but it does help give you a little bit of leeway. Also, the other thing you can do is you can reduce the load on the CPU on your host. Okay, so if your host VI is using a lot of CPU, or other things on your host computer are using a lot of CPU, that could slow down how fast the host VI is able to grab elements out of the FIFO. So by lowering the CPU usage, you could potentially increase the speed of how fast your host VI takes things out of the DMA FIFO. So how do you identify a DMA FIFO overflow? The way you could do this is, here we have a block diagram of our FPGA VI, and then on our FPGA VI we're writing to a DMA that is going from the target to the host. So in this case, notice that there is a timed out. Okay, so as we're trying to write some data to it, if the DMA FIFO is already full, then that write node over there is going to timeout, and timeout is going to be true. And then notice over here we're using a feedback node to latch whether or not a timed out condition has ever happened, and we're outputting that to an overflow indicator. Because we have an overflow indicator, now our host VI can use the read-write control function to find out the status of that overflow indicator and see if it's true or false. Also, I just want to note that it's very important to latch the overflow, as overflow typically won't be persistent. So if you're looking at it and you're not latching it, the overflow LED or the overflow indicator might go true just for a second and then go back to false. But if you're looking for overflow, you really want to check if the overflow ever happened, because you want to know if it even happened once, then you know you've lost some data, and your data possibly could be processed out of order. So make sure you latch that overflow when you're checking for it. Okay, so let's say you've detected that you've had an overflow on your DMA FIFO. Well, how do you recover from it? We're going to talk about two primary methods that you can deal with that. So one way you can do it is you can reset the FPGA VI, and what that'll do is it'll clear your DMA FIFO and discard all the data in your DMA FIFO. So pretty much now you have a fresh DMA FIFO to restart from. The other way you can do it is you can flush the buffer programmatically. So for example, in your program, if you know you have an overflow, you can immediately just empty the FIFO by reading all the remaining data in that DMA FIFO, and you can either keep it or you can discard it depending on what's appropriate for your application. So the flushing buffer method or the resetting the FPGA VI method, you can use either of these to either recover from a DMA FIFO, or you can also use them to initialize your DMA FIFO at the beginning of the execution of your program, just to make sure that you're starting with a clean and empty DMA FIFO. Okay, so let's talk about clearing the DMA FIFO using the reset method. Okay, so there is an invoke node method that you can use called reset, and if you call this, then that'll actually reset your FPGA VI to its default state, which means it'll also clear all the DMA FIFOs and the FIFO information. So one thing I wanted to warn you about, so if you're testing out your FPGA VI and you're doing execution on your development computer, like you should, the behavior here is the FIFOs will automatically reset when the VI stops and restarts. Okay, this is not indicative of what happens if you're actually executing on the FPGA target. If you're executing this and it's compiled and it's running on the FPGA target, the FIFOs do not automatically reset between starting and stopping. So to reset your FIFOs properly programmatically, you can either use the invoke method function and choose the reset method, or you can also use the close FPGA VI reference function, and you want to make sure that it's configured for close and reset if last reference. So typically I like to put the reset method at the very beginning of my VI. That way I can ensure that I'm clearing that DMA FIFO and starting from a clean state. So in this slide we see an example of using the reset FPGA VI method to reset the FPGA VI at the very beginning. So notice we're on our host VI. We've opened a reference to our FPGA VI, and then we're passing that reference to reset. So the first thing we're doing is we're opening up that FPGA VI, then we are resetting it to make sure that the DMA FIFO is clean and is empty. And then we are configuring our DMA and asking for a host buffer size. And then we're going to go ahead and run it again. So once we've reset it, we've stopped the actual FPGA VI from running. So later on, we have to go ahead and do a run method to make sure we have the FPGA up and running before we enter the main part of our program. Okay, now let's talk about the clearing a DMA FIFO by using the flush DMA FIFO buffer method. Okay, so if you want to clear a DMA FIFO this way, then the first thing you need to do is you need to stop writing to your DMA FIFO. So let's say we had an overflow condition. First thing you want to do is stop writing to that DMA FIFO. The next thing you want to do is you can find out how much data is remaining in that DMA FIFO, and then if you read all the remaining elements, then you can empty that DMA FIFO. Okay, so if we look at that block diagram on the bottom, what we're doing is we assume that at this point we've already stopped writing to the DMA FIFO, so it's not going to get any new elements at this point. And then we're just quickly checking how many elements are remaining in that FIFO, and then we're going to read all of them. And notice that we flushed the remaining elements to that indicator data. Okay, and then at that point we can either choose to throw it away or maybe we can store it somewhere, depending on what's appropriate for you. So in exercise 11.3, I would highly recommend that you do this one. We are going to write an application where we are acquiring data on the FPGA VI, and then we're going to transfer that buffer data to a Windows host VI. And we're going to use a lot of the different methods that we talked about in this section. And we're actually going to get even more detailed into it and demonstrate a way of handling overflow that wasn't necessarily discussed in the slides, but it's a nice detailed implementation of it based on the methods we talked about in this section. So definitely try this out, and you can take a look at the solution module as well if you want to look at the details.